welcome to IACE. So today we are going to discuss RRB JE Civil Engineering point of view CBT 2. So today we are going to discuss one of the important subject in the civil engineering point of view for the CBT 2 of RRB JE. So here, RCC, reinforced cement concrete. So this is the one of the important subject in the civil engineering point of view in all examinations, not only the RRB JE, in SSC JE and state PSUs like AE, AWs and all the examination. So the weightage of this subject in the RRB JE point of view, so weightage is 7 marks is the weightage, and including the material part, so that is including the concrete technology. So the weightage of this concrete technology is 8 marks. That means in the RCC, reinforced cement concrete, one is the design part and one more is concrete part, that is material part. So for the only the design part of the RCC, it consists of 8 marks, and including the material part, so the weightage is 8 marks. So total weightage of this subject is 15 marks is the weightage. 15 marks weightage of this subject. So 7 marks for only the RCC, and the material part is the concrete part is 8 marks. So completely, so it is the 15 marks weightage. That means so in all the examinations, so this is the good weightage subject. So in this RCC, one is the design part and one more is material part. So in this design, so we are going to learn different methods. So like limit state method, ultimate load method and working stress method. So in all the method, so we discuss now one by one, so each of the methods. So the first one is design methods. Design methods. So design methods. So in this design methods, generally reinforced concrete structures, reinforced concrete structures are generally design so by using 3 different methods. One is a working stress method. So the first method is working stress method. This working stress method also known as elastic method. This working stress method also known as the elastic method, and the one more name of this working stress method is modular ratio method. That means working stress method also known as elastic method, and this working stress method also known as the modular ratio method. And the second type of method is ultimate load method. This ultimate load method we call it the load factor method. And the third method of design and the very important method is limit state method. Right, so in the design point of view, so all the reinforced concrete structures are designed by using the 3 different methods. One is working stress method, second one is ultimate load method, and third one is limit state method. So among these three methods, so working stress method and limit state method used for design point of view, but ultimate load method is not used so in the design point of view. So let us learn each of these methods in details. So let us take working stress method. Right, so let us take a working stress method. The first method is a working stress method. Working stress method. The first method is a working stress method. In the short form, we write as WSM. Right, so working stress method. So this working stress method, we know working stress method is also known as a elastic method, also known as a modular ratio method. So working stress method, it is the traditional method of design. It is the traditional method of design. It is the traditional. It is the traditional method of design. Traditional method of design. Why it is called the traditional method of design means it is the first and oldest method. It is the first and oldest method because it is the first and oldest method. It is the first and oldest method. That's why it is called as the traditional method. So this method came into consideration in the year 1900. So this is the first method of design. So and the second one is it is the first method. It is the first method. It is the first method. It is the first method accepted by all the national courts in India. All the national courts. All the national courts. Right, so it is the traditional method of design and it is the first method accepted by all the national courts. And so the third one is the third point is so working stress method used for design of concrete structure and design of timber structure and design of steel structure. That means working stress method not only applicable for design of RCC structures but also applicable for design of timber and steel structures. Right, so working stress method not only applicable for the design of not only applicable for the design of RCC structures. Design of RCC structures. Design of RCC structures. But also applicable for design of timber and steel structures. Right, so this working stress method not only applicable for the design of RCC structure but also applicable for the design of timber structure and the design of steel structure also. Next point. So working stress method working stress method, it gives sufficient safety. It gives sufficient safety. Right, so it gives sufficient safety by restricting the stresses in the material. By restricting the stresses, in materials. So working stress method, it gives the sufficient safety by restricting the stresses in the material. And one more point in the working stress method is, working stress method, it is the stress governing method. Working stress method is a stress governing method. Working stress method is a stress governing method. And in the working stress method, so it always follows the elastic theory. Working stress method is based on elastic theory. That's why it is called as the elastic method. And the very important point in this working stress method is factor of safety. The factor of safety for the steel and concrete in the working stress method is the factor of safety for steel is 1.78 and the factor of safety for concrete is 3. Here the factor of safety, the factor of safety for steel, and the factor of safety for concrete. In this method, the factor of safety for steel and the factor of safety for the concrete is 1.78 and 3. 1.78 and 3 respectively. That means factor of safety for steel is 1.78. It is approximately 1.8. So as per Indian Code of Practice, it is 1.78. So for the steel and 3 for the concrete. But here, so I have one doubt, that is why the factor of safety for a steel is less compared to the factor of safety of concrete. That means here the factor of safety is required for concrete is more compared to the steel, because the factor of safety for in the working stress method, the factor of safety for concrete is 3. The factor of safety for steel is 1.78. So remember this factor of safety value. So this is asked in various examinations, right? So factor of safety in the working stress method, so steel's factor of safety is 1.78 and the factor of safety for concrete is 3. So because for the concrete, the making of various concrete members within the open atmosphere only, and for the making of steel reinforcement within the closed portion in the industries only. That's why the factor of safety required for steel is less compared to the concrete. Right, here the factor of safety for steel is 1.78 and the factor of safety for concrete is 3. But what is the factor of safety? What is the factor of safety? So the factor of safety, it is the ratio of yield stress of the material to the corresponding working stress of the material. And one more, so it is the ratio of ultimate stress of the material to the corresponding working stress of material. So factor of safety, the factor of safety for so the factor of safety, so definition, factor of safety, right? So factor of safety, it is the ratio of yield stress of the material. It is the ratio of yield stress of the material to the corresponding working stress of the material. Otherwise, it is the ratio of ultimate stress of the material corresponding to the working stress of the material. So first one is ultimate stress of the material upon working stress of the material. Working stress of the material, right? So factor of safety, ultimate stress of the material corresponding to the working stress of the material. One more is factor of safety is equal to yield stress of the material, corresponding to the working stress of the material. So here, so the factor of safety, ultimate stress upon working stress. One more is yield stress upon working stress. Here, factor of safety, ultimate stress upon working stress and yield stress upon working stress. Both are correct only. But yield stress upon working stress is applicable for which type of materials, and yield stress of the material, yield stress corresponding to the working stress is applicable for which type of the material. Here the ultimate stress upon working stress, it is applicable for brittle material. It is applicable for brittle material, right? So brittle material means so chalk piece is the brittle material and plain concrete PCC is the brittle material. So the example of brittle material is so PCC, simply we call as concrete. So concrete is the best example of so brittle material. So concrete, that means plain cement concrete. The ingredients of binding material, fine aggregate we call as the sand, and coarse aggregate mixed with water, it is called as concrete, right? So concrete we know, so concrete is the plain cement concrete, or simply we call as the concrete. So it is the ingredients of binding material cement, fine aggregate we call as the sand. One more is so coarse aggregate, fine aggregate, coarse aggregate added with water, right? So this is called as the concrete, or simply we call it the plain cement concrete. And this factor of safety, ultimate stress of the material corresponding to the working stress of the material. So it is applicable for ductile material. It is applicable for ductile material. What is the best example of ductile material, my dear? So the best example of ductile material is reinforcement, simply we call as steel. Steel is the best example of ductile material. That means here if we apply the load, so here we apply the load. For example, this is the brittle material. When we apply the tension force on the brittle material, it simply fails. And when we apply the compression force, it resists some force, compression force. But if you apply the tension load on the brittle material, it fails simply. Without prior warning, it fails suddenly. That is the brittle material. To resist the sudden failure in the concrete member, we add the reinforcement bars. That is called as the reinforced concrete. Plain concrete. So if you take the cubes, plain concrete cubes, if you apply the compression load, right, so by using the UTM, universal testing machine, or simply compression machine, if you apply the compression load, it will take some compression loads. But if you apply the tension load on the brittle material, example, so one of the concrete member, it fails suddenly. And ductile material, for example, if you take reinforcement, that is bars, iron bars, steel bars, if you apply the tension load on the reinforcement, it is not fails suddenly. If you apply the tension load on the reinforcement bars, if you apply the tension load, it elongate, and finally it fails. How it fails? Reinforcement bars are fails cup cone failure. That means one side formed as cup, one more side formed as cone. Right? So ductile material, duct means thin wire. When we apply the tension load on the reinforcement bar, it elongates. That means the diameter of the reinforcement bar is reduces, then it is fails. That is called as the ductile material. The best example of the ductile material is steel reinforcement, or simply steel bars. Right, so factor of safety, ultimate stress upon working stress, and factor of safety, yield stress upon working stress. Ultimate stress upon working stress applicable for brittle material, and this yield stress upon working stress applicable for ductile material. Right, so this is the factor of safety. So very important in our examination point of view. But so this working stress method, some drawbacks is there in the working stress method. Right, so drawbacks in the working stress method. So what is the drawback of a working stress method? So drawbacks in a working stress method. In the working stress method, some drawbacks is there in the working stress method. Because after the working stress method, now we use the limit state method. That means for the design of this concrete members, we use IS 456-2000 code, right? IS 456-2000 code. So here the drawbacks of a working stress method. In this working stress method, so there is neither true strength nor true factor of safety. Right, so in this working stress method, so gives neither true strength nor true factor of safety. That means so it gives neither true strength neither true strength nor it gives neither true strength nor it gives so neither true strength nor gives the true factor of safety in the design. Here so it working stress method neither gives true strength nor gives true factor of safety. It means from the experiments point of view, if you take a Fe 250 grade of steel, if you take Fe 250 grade of steel, so for this Fe 250 grade of steel, if you so determine the yield stress, that is 0.87 times of Fy, 0.87 times of Fy. That means 0.87 into what is the Fy value? Characteristics yield strength value is 250 Newton per mm square, right? So 250 Newton per mm square. Right here, so 250 Newton per mm square, 250 Newton per mm square, because we take Fe 250 grade of the steel. So then we get so 217.5 Newton per mm square value only. This Newton per mm square also known as megapascal, right? So it is the megapascal. Right, so from the experiments point of view, if you take Fe 250 grade of steel, so 0.87 times of Fy, that is so we multiply the 0.87 times of Fy, that is the grade of the steel 250, then finally we get 217.5 Newton per mm square. This is based on, this value is based on experiments point of view, but so IS code IS 456 gives the value. So as per IS codes, as per IS code, the yield stress value is so yield stress value is 140 Newton per mm square, right? So 140 Newton per mm square. That means from the experiments point of view is 17.5 Newton per mm square, and as per IS code values, that means IS 456 2000 gives this 140 Newton per mm square for Fe 250 grade of steel. So here, so the too much variation is there, right? So that's why working stress method gives neither a true strength nor gives a true factor of safety. This is one of the drawback of working stress method. And the second drawback of working stress method is so here, so in the working stress method, the second drawback is in the working stress method of a design, the second drawback is in a working stress method of design, in the working stress method, so modular ratio, the modular ratio design, the modular ratio design, the result of compression, the result of percentage of, the result of so percentage of compression steel, percentage of compression, the result of compression steel the result of compression steel is more than a limit state method. Limit state method. Here in the working stress method, modular ratio design, the result of percentage of compression steel is more than a limit state method. More than the limit state method. For example, if you take the cross section of a simply supported beam, take the cross section of simply supported beam. So this is the cross section of simply supported beam, and this is the neutral axis. This is the neutral axis. Above the neutral axis, this is the top fiber. Below the neutral axis is the bottom fiber. So here in the top fiber, so we add only to reinforcement, and the bottom fiber, due to the tension applied, that means to resist the tension, the cross section of simply supported beam means so in the bottom side the tension is develops, in the top fiber so compression is developed. So to resist the tension, so we add the reinforcement more in the tension zone, right? So this reinforcement we call as AST, that means area of tension steel. And so this side reinforcement in the compression fiber we call as ASC, that means area of compression steel. But this is the working stress method. It always follows the modular ratio value. That's why here M into AST. That means M times of area of tension steel. But here also M into ASC, area of compression steel. But here in the working stress method, due to the result of creep, due to the creep effect, here we add one additional bar, right? So in the compression zone, so we add one additional bar, right? So one additional bar, so this is additional bar is provided. Additional bar is provided to resist creep, to resist the creep. One additional bar is provided here, right? So one additional bar is provided means in the compression fiber 1.5 times of modular ratio. Here M is equal to modular ratio. Modular ratio. That means so here in the working stress method, so modular ratio design, the result of a large percentage of the compression steel, so compared to the limit state method. So here only 2 bars are so enough, right? So 2 bars are enough, but due to the creep effect, so here one more additional bar is required to resist the creep. So what is the creep? A sustained or long-term load is applied on the member. It will bend, or it will bend due to the sustained or long-term load is applicable on the member. So it is called as the creep. The sustained or long-term load is applied on the member. Due to the application of long-term load, due to the application of constant load, it bend like this. This is called as a creep effect. Alright, so due to the creep effect, one additional bar is required in the compression zone. So that's why, so here in the modular ratio design of working stress method, large percentage of compression steel required compared to the limit state method, right? And so one more is the third one is, the third drawback is, so this is one more drawback, right? Additional bar is required is one more drawback. Right, the third drawback is in the working stress method because of non-linear stress strain and creep of the concrete. Because of non-linear stress strain curve and creep of the concrete. The result of right, so the result of here stress strain curve, the result of non-linear stress strain curve because of non-linear stress and strain curve. So because of non-linear stress and strain curve, because of non-linear stress and strain curve, because of non-linear stress and strain curve and creep of concrete. Right, so because of non-linear stress and strain curve and so creep of the concrete, so there is no definite modulus of elasticity. Modulus of elasticity. Modulus of elasticity. Right, so the third drawback is because of non-linear stress and strain curve. Because of non-linear stress and strain curve and creep of the concrete, there is no definite modulus of elasticity. That means non-linear stress and strain curve and creep effect. So due to these problems, there is no definite modulus of elasticity. For example, if you take steel reinforcement, stress and strain curve for steel. Right, so we know in the y-axis, so stress, we take the stress, it is denoted with sigma, and in the x-axis it is strain, so it is the strain, that is epsilon. Write the stress in the y-axis and the strain values in the x-axis. So this is the origin point 0. 0 is the origin point. So from the origin, if you take the steel, a steel reinforcement, so the steel reinforcement is so up to proportionality limit, the stress is directly proportional to strain. That means it is linear. The steel is linear. Right, so it is linear. It is linear. So it is linear. Then it is curved. So from the origin point, so here, so proportionality limit. Up to proportionality limit, the stress is directly proportional to strain. The stress is directly proportional to strain. Up to proportionality limit, the stress is directly proportional to strain. That means stress upon strain we call as the modulus of elasticity, also known as Young's modulus. Right, so up to the proportionality limit, the stress is directly proportional to strain. That means so up to origin, from the origin to proportionality limit point, so this so graph, that means this line is very straight. Right, and here so elastic limit upper yield point, and this is the lower yield point. This is the lower yield point. At the lower yield point, so the strain value is, at the lower yield point, the strain value is 0.2%. It is taken as 0.002. At the lower yield point, the strain value of steel is 0.2% of strain value. And at the failure, so this value is 0.0035 at the failure point. The strain value of steel at the failure point is 0.0035. So at the lower yield point, because in the design point of view, we take the lower yield point value. In the design point of view, we take a lower yield point, that is 0.2% of strain or 0.002. Right, so this is very important in the examination point of view, asked in the various examination. And this is so the at the failure point, so the value of the strain is 0.0035. It is also very important. So this is the stress and strain curve of the steel, but we need the stress and strain curve of the concrete. Here we take the stress and strain curve of the concrete. Stress and strain curve of the concrete. So we know the y-axis we taken as stress, and on the x-axis we taken as strain. So this is concrete, right? The stress and strain curve of the concrete. So here from the origin, if you take the load, if you apply the load, so this is if you apply the load, this is like this. That means so here proportionality limit is not develops in the concrete, because if you apply the load, it is fails simply because it is a brittle material. So because of this non-linear stress and strain curve of the concrete, so we develop the stress and strain curve, and so from the stress and strain curve we determine the modulus of elasticity value. To determine the modulus of elasticity value from the origin point of this stress and strain curve, so we draw the tangent from here. We draw the tangent. So one is from the origin point, so we draw the tangent here. We draw the tangent here. So this tangent we call it the initial tangent modulus. This is we call it the initial tangent modulus. Initial tangent modulus. Right, so from this initial tangent modulus, we develop the stress and strain. That means from the stress and strain curve, we determine the modulus of elasticity value. Right. Here take one point here on this non-linear graph. Here take one point. Again draw the one tangent here. Draw one tangent. This is simply we called as tangent modulus. Tangent modulus. Tangent modulus. Right. Again from the origin, here take one point from the tangent. So from the origin here take one point and draw the one tangent. Draw one tangent. So this is we call as from this tangent we develop the stress and strain curve. We develop the stress and strain. Then so stress is directly proportional to strain. Stress is directly proportional to strain means modulus of elasticity. Stress upon strain means modulus of elasticity. This point we call as this point we consider as 0.002. That 0.002 or this value is 0.2%. 0.2%. Right, so this value is 0.002. So this tangent we call it the secant modulus or modulus of elasticity or short term modulus. So this tangent we call as the secant modulus, also known as short term modulus. Right, so the third drawback is because of non-linear stress and strain curve and creep of the concrete, there is no definite modulus of elasticity. So here, so in the concrete member, so we are not develops the modulus of elasticity. That's why we take the tangent. First we take the tangent here. This is called as the initial tangent. We take the tangent on the graph. That is the simply we call it the tangent modulus. And so here take one point. So on the graph and from the origin point. So we draw the tangent. This is called as the secant tangent modulus, or simply we call it the short term modulus. So this short term modulus, from the secant modulus and short term modulus, we develop the modulus of elasticity. So we develop the modulus of elasticity. Right, so we develop the modulus of elasticity, that is we take as E is the modulus of elasticity or Young's modulus. What is the modulus of elasticity? It is the ratio of stress upon strain. It is the ratio of stress of the material corresponding to the strain. Stress upon strain, so we consider as modulus of elasticity. So this modulus of elasticity, so we determine from the secant modulus or short term modulus. Right, so modulus of elasticity. And one more, what is the secant modulus and what is the short term modulus? Right, so the first one is secant modulus. Secant modulus, it is also known as short term modulus. Short term modulus, it is denoted with EC, short term modulus. Right, so secant modulus or short term modulus. This secant modulus are develops due to the short term loads. Short term load means so live load is the short term loads, right? So due to the various live loads, so this short term modulus or secant modulus develops. So the short term modulus is equal to so 5000 under root of FCK. 5000 under root of FCK Newton per mm square or megapascal. Right, so for determination of short term modulus or secant modulus, as per the Indian Code of Practice, this is as per Indian Code of Practice, as per IS 456-2000 code. IS 456 so 2000, as per IS 456-2000, as per IS 456 code, so this is the short term modulus or secant modulus, so 5000 under root of FCK. So this short term modulus are developed due to the short term loads. Here, so where FCK, so where FCK is equal to characteristics cube compressive strength. Characteristics cube compressive strength after 28 days of curing. After 28 days of curing. After 28 days of curing. Right, so this FCK is the characteristics cube compressive strength. FCK is the characteristics cube compressive strength after 28 days of curing. That means here take one cube, and one more cube, and so one more cube. So what is the size of this cube, concrete cube? That means 15 centimeter into 15 centimeter into 15 centimeter size of the concrete cube. Take so 1, 2 and 3 cubes. Take the 3 cubes. Then so these 3 cubes, 1 cube, second, and this 3 cubes, take the 3 cubes compressive strength, average strength. Right, so after 28 days of curing, so make this cube and so pour in the water, right, and after 28 days of curing, so if you apply the compression load, so that is the FCK value, the average of these 3 cubes value we call as the FCK, characteristics cube compressive strength, after 28 days of curing. Right, so but if you take so secant modulus or SATA modulus, for example, if you take, for example, take M25 grade of concrete, M25 grade of concrete. For M25 grade of the concrete, what is the secant modulus or SATA modulus values? For M25 grade of the concrete, what is the SATA modulus or secant modulus? So for the SATA modulus or secant modulus of this M25 grade of the concrete means 5000 into under root of FCK Newton per mm square, we know Newton per mm square. Right, so apply the values here. 5000 under root of FCK, that means under root of 25. So root 25 value is 5, right? 5 5s are 25. So 5 square, that means square root is cancelled. Then so it is 5. Root 5 means the value is 5. Right, so here 5000 into 5 means 5 5s are 25,000. 25,000 Newton per mm square. 25,000 Newton per mm square, or simply we call as the 25,000 megapascal. Megapascal means the value is 10 to the power of 6 is the megapascal, right? So megapascal means 10 to the power of 6. So this is we write as 25 gigapascal also, right? 25 gigapascal. Megapascal means 10 to the power of 6. Gigapascal means 10 to the power of 9. So that's why 25 gigapascal. So the M25 grade of the concrete secant modulus or SATA modulus or modulus of so this concrete. So secant modulus or SATA modulus value is 25 gigapascal. Right, and one more is long term modulus. The second one is long term modulus. Long term modulus. Long term modulus. Right, so long term modulus, so it is called as the effective modulus also. Effective modulus. Effective modulus. Right, so it is denoted with ECE. Right, so long term modulus or effective modulus. So what is the long term modulus? It is the ratio of short term modulus upon 1 plus so creep coefficient value. So ECE is equal to long term modulus is equal to SATA modulus upon 1 plus creep coefficient we denoted with theta. Right, it is equal to 5000. What is the SATA modulus? 5000 root of FCK. 5000 into under root of FCK upon 1 plus theta. This is the long-term modulus. This value, this formula for the determination of long-term modulus or effective modulus. So here, we know the FCK, characteristics strength, compressive strength, characteristics cube compressive strength after 28 days of curing. And here theta is the creep coefficient. Creep coefficient. So here the long-term modulus are develops due to the long-term loads. What is the long-term loads? Dead load is the long-term load. Right? So secant modulus or short-term modulus is developed due to the short-term loads. That means changeable loads like live loads. But so this long-term modulus or effective modulus are developed due to long-term loads or constant loads. The example of the long-term load is, so dead load is the long-term load. Right? So this creep coefficient, the creep coefficient theta is the creep coefficient, right? That the creep coefficient is depends upon age of the concrete. The creep coefficient is depends upon age of the concrete. That means here theta creep coefficient it is depends on so depends on age of concrete. It is depends on the age of the concrete. That means creep coefficient values is depends upon age of the concrete. For example, if you take age of concrete, if you take the age of the concrete and the creep coefficient value, age of the concrete and so creep coefficient values. For example, if you take the age of the concrete, that is so 7 days age. For the 7 days age, what is the creep coefficient value? The creep coefficient value as per code IS 456. So the creep coefficient value for 7 days age of the concrete is 2.2. And for 28 days strength, the 28 days age of the concrete, what is the creep coefficient values? Right? So for 28 days it is 1.6. And for 1 year, for the 1 year age of the concrete, the creep coefficient value is 1.1. The creep coefficient value is 1.1. So simply remember here, the age of the concrete, the creep coefficient values is depends upon age of the concrete. That means if the age of the concrete is increases, then the creep coefficient values decreases. The age of the concrete is increases, then the creep coefficient values decreases. Here the age of the concrete, 7 days age of the concrete, the creep coefficient value is 2.2. Here the age of the concrete is 28 days, that means 1 month age of the concrete. For the 28 days of the concrete, the creep coefficient values is so here 1.6, and the age of the concrete is 1 year. For the 1 year age of the concrete, the creep coefficient values for the 1 year age of the concrete, the creep coefficient value is 1.1 is the creep coefficient value, right? So remember the 7 days creep coefficient value, 7 days age of the concrete is 2.2, and 1 year means so for 1 year age of the concrete, so the creep coefficient value is 1.1. Here 1 year, that's why it is 1.1. So this is 28 days, that means 1 month age of the concrete. So add this all the values, 2 plus 2 is the 4, 4 plus 1, 5, 5 plus 1, it is 6. So simply we write as 1.6 is the, so 28 days age of the concrete. 28 days age of the concrete. Remember the 7 days age of the concrete is 2.2. These values as for the code only, IS 456, so code IS 456 2000 codes. The creep coefficient is depends upon age of the concrete. If the age of the concrete is increases, creep coefficient values decreases. The 7 days age of the concrete, the creep coefficient value is 2.2, and for 1 year the age of the concrete, here 1 year means 1.1, remember. For the 28 days, that is 1 month, for the 1 month age of the concrete, it is 1.6. So if it is so confused, then remember 2.2 means add 2 plus 2, 4. Here 1.1 means add 1 plus 1. Here 4 plus 1 plus 1, 6. So here 2 plus 2, 4, 4 plus 1, 5, 5 plus 1, 6. So simply we write as 1 point, simply we write as so here 1.6, second one, not the first one, the second one is 1.6. So this is the age of the concrete. Clear? So this is so the drawback, one of the drawback. Next, the last one is so modulus of elasticity. Modulus of elasticity or Young's modulus. So it is the ratio of stress upon strain is we derived from the stress strain diagrams, right? And the fourth one is right. So modular ratio. The modular ratio we determine. What is the modular ratio? Modular ratio. Right. So modular ratio M is equal to modular ratio. Right. So modular ratio M is equal to, so it is the ratio of modulus of elasticity of steel. Modulus of elasticity of steel upon modulus of elasticity of concrete. Modular ratio is equal to modulus of elasticity of steel upon modulus of elasticity of concrete. Otherwise, largest modular ratio value upon smallest modular ratio value. But in the working stress method, modulus of elasticity of steel, modulus of elasticity of concrete is not so possible to determine the modular ratio. So here in the working stress method, modular ratio M is equal to 280 upon 3 sigma CBC. 3 sigma CBC. Right. So modular ratio M is equal to 280 upon 3 sigma CBC. This is very, very important for our examination point of view. 280 upon 3 sigma CBC. Here, so sigma CBC, where sigma CBC, where so sigma CBC is equal to permissible bending compressive strength. Permissible bending compressive stress in concrete. Permissible bending compressive stress or permissible bending compressive strength of concrete. Permissible bending compressive strength of concrete or compressive stress of concrete. So here, so modular ratio is equal to modulus of elasticity of steel upon modulus of elasticity of concrete is not possible here in the working stress method. This is one of the drawback. So here the modular ratio is equal to, so 280 upon 3 sigma CBC is the modular ratio. Here sigma CBC is the permissible bending compressive strength of concrete, or permissible bending compressive stress of concrete. Right, so these are the various drawbacks in working stress method. Right, so in the next class we will learn so the assumptions in the working stress method. So assumptions in working stress method. Right, thank you.